introduce our next speaker, Sola from Stockholm University, who will talk about local theory for stable polynomials with applications to integrability for rational functions of several variables. Alan, please.
Thank you very much. Let me start by thanking the organizers for presenting me with an opportunity to speak at the Fields Institute. So it's kind of a funny thing. I've been to Toronto many times to visit family, but I've never given a talk in Toronto. So this is a first. So what I'll be talking about today is based on joint work with Kelly Bickle, Greg Neese, and James Pascoe. I'm in the fortunate position of having had some of the things that we'll be talking about today anticipated by Greg in his excellent talk yesterday. So my title is Local Theory for Stable Polynomials with Application to Rational Integrability for Rational Functions of Several Variables. So let me start by recalling what a stable polynomial is in this context. So we can make it the general definition. If we have some domain in CD, then we simply say that a multivariable polynomial is stable in the domain omega if P has no zeros in omega. So later we'll specialize to certain domains of product type, but this basic definition is valid for any domain. So just to give you an example, and this example will give us some of the, or most of the examples that we'll consider in this talk. This is a polynomial 2 minus z1 minus z2. And if you look at the set of points in C2 where both coordinates have modulus less than 1, then you can check quite easily that this polynomial has no zeros in that domain. And this domain is called the bidisk. So the other objects that we'll be considering in this talk, other than stable polynomials, are so-called bounded rational functions. So we say that a function of the form q divided by p, where both p and q are multivariable polynomials, is a bounded rational function in omega if f is analytic on omega and its modulus is bounded for all points in omega. So an example of this type of function would be the function that I've written down here, 2z1 z2 minus z1 minus z2 divided by 2 minus z1 minus z2. You can check by hand that this function has modulus bounded by 1 in the bidisk, the set of points in C2 where both coordinates have modulus at most 1. So in order for f of this form to be analytic in omega, the denominator polynomial p cannot vanish in omega, and so is a stable polynomial. So there's a connection between stable polynomials and bounded rational functions via denominators. So a basic question that one can ask as regards these bounded rational functions is this: if you give me some stable polynomial p, what are the possible choices for q such that q divided by p furnishes a bounded rational function in omega? So again, we could in principle consider this question in quite general domains, but we'll specialize to polydisks and poly upper half planes for reasons that will become apparent later on. So if P has no zeros on the closure of omega, well, then Q divided by P is bounded for any choice of polynomial Q. And so the interesting situation arises when P is stable, but not strongly stable in the sense that P is non-vanishing on the closure. So if P has some zeros on the boundary of omega, then this question becomes quite interesting. So as a little warm-up exercise, let's think about what this would mean in one variable. So in one variable, if you have some zero at the boundary point zeta naught, well then Q divided by P is going to be a bounded rational function precisely if the numerator polynomial vanishes to at least the same order as the denominator polynomial. So you can factor out zeros in one variable. So this question, it doesn't really have much interest in that situation, but when you're in higher dimensions, then this question becomes subtler and more interesting. So the basic reason here is that you can't standardize zeros of a function of several variables in the same way that you can consider factors of the form z minus zeta naught in one variable. Another thing that we'll discuss in the course of this talk is the following sort of higher order question. If you do have something of the form q divided by p, where q and p are polynomials and this function is bounded, does that entail any additional regularity other than boundedness? So there are many different ways you could measure this, but one way would be to say, okay, so q divided by p is a bounded function, and we could compute its derivative with respect to z1, say, and ask if this is regular in some sense. And one way of making this precise is to ask whether there is some range of exponents such that the derivative is NLT. Okay, so just to give you an idea of what's going on here, let's look at some examples. So here is one rational function of two variables. I've taken the same polynomial that I examined earlier, namely 2 minus z1 minus z2. And as a numerator polynomial, I've picked z1 minus 1. The question is this bounded in the bidisk? And it turns out that the answer is no, this function is not bounded. Okay, so what if I throw in another factor? So in this case, z2 minus 1. Well, then it turns out that I get a function that is bounded in the bidisk. And the thing to note here is that all the polynomials involved in the numerator and the denominator here have a 0 at the point 1, 1, which is an element of T2, the Cartesian product of two unit circles. And typically, when you think about function theory in polydisk or poly half planes, it's a distinguished boundary that is critical as regards boundary behavior. And the distinguished boundary in the case of the bidisk is exactly T2. Okay. So let me start off by telling you about a sample theorem from our paper. And it is this. So if q divided by p is a bounded rational function in the polydisk, in d to the d, then the non-tangential limit of f exists at every point of t to the d. Non-tangential here means that the variables approach the boundary non-tangentially in each variable. So this is a strengthening of the Fatou theorem in the sense that knowing that f is bounded immediately guarantees existence of non-tangential limits at almost every point. But the point here is that the exceptional set turns out to be empty for bounded rational functions. And this is a generalization of a result that was obtained earlier by Nice for rational inner functions. And these are rational functions on polydisks that have modulus equal to 1 at almost every point of t to the d. Okay. So boundedness of a rational function implies some additional regularity in this sense. Non-tangential limits exist at every point of the distinguished boundary. But the situation is not as nice as you might think in the following sense. So if p has zeros on the distinguished boundary, then a bounded rational function does not extend continuously to the closure of the domain in question. And so we can see this for the example that we looked at earlier, this function z1 minus 1 times z2 minus 1 divided by our favorite polynomial 2 minus z1 minus z2. So if you set z1 equal to 1, then the numerator is 0. So there are certainly some points, some ways of approaching T2 where this function is 0. But if you plug in z2 equals z1 bar, then this entire expression turns out to have modulus equal to 1. So this function cannot possibly be continuous on T2. So bounded rational functions are regular in some sense. They have non-tangential limits at every point, but they need not be continuous functions on the closure. So returning to this question of devising numerators for bounded rational functions, let's ask ourselves if there are any obvious choices that we can make here. Well, so the most obvious choices of them all is to just say that I'm going to pick Q as some polynomial multiple of P. Well, then the function I get is just that polynomial multiple, and so clearly this is a bounded function on a polydisk. So one thing that is perhaps a little bit more interesting is doing the following. I'm going to pick Q as a polynomial multiple of a certain polynomial P tilde, which is built out of P. So how do you get this P tilde polynomial? So in the context of a polydisk, what you do is that you evaluate your given polynomial P at the point 1 over Z bar. And then you take the complex conjugate of that. And then in order for this to become a polynomial, you multiply through by the monomial factor Z1 to the N1 ... ZD to the ND. So you look at the degree of P in the individual variables, and you multiply through by a monomial factor to get a reflected polynomial P tilde. So this is going to give me a function f, which is of the form r times P tilde divided by P. And if you attended Greg's talk yesterday, you might remember that this P tilde divided by P is exactly a representation for rational inner functions in polydisks. And so P tilde divided by P is going to have modulus 1 on the D torus, and that means that R times this function is a bounded rational function on the polydisk D to the D. Now I can form linear combinations of objects of this form. So in algebraic terms, I could consider the numerator polynomials that are that belong to the ideal generated by the polynomial P and the polynomial P tilde. And that's picking such a numerator is also going to give me a bounded rational function. So it's for this reason that looking at this question in the polydisk and later in the poly upper half plane is particularly enticing, because there are ways of generating these numerators in a systematic way. If you give me some general domain omega, it's not so clear how to pick interesting numerators. Well, of course, you could pick multiples of P itself, but this reflection operation is connected with the nice symmetries that are present in the case of the polydisk or the poly upper half plane. Okay, so we have some way of devising numerators for rational functions that we want to be bounded. And of course, once you figured out one way of doing this, you might ask, well, is this it? Okay, so in this talk, we'll see at least partial answer to this question. But in order to do this, I am going to have to specialize to 2 dimensions. And omega here is going to be one of 2 conformally equivalent domains, namely the bidisk and the bi upper half plane H2. So just to recall, the bidisk is the set of points in C2, where both coordinates have modulus at most 1 or less than 1. And the poly upper half plane is the set of points in C2, where the imaginary part is positive. So because of Bezout's theorem, I can reduce to the case where P has finitely many zeros on the distinguished boundary. And in order to make the question interesting, we're typically going to assume that there are such boundary zeros. And so polynomials that are stable of this type, in our paper, we call them pure stable or atorial stable, if you prefer. As a normalization, I might as well assume that the 0 in the bidisk setting is sitting at 1, 1, because this is a local question initially. If I can make sure that my rational function is bounded at all, each individual 0 of P, then it's going to be bounded. Okay, so here is a very partial answer to this question. So I formulated it as saying that if P is generic pure stable, In technical terms, that means that the order of vanishing of P is exactly 1 at each of its boundary zeros. Then Q divided by P is bounded near 1, 1, exactly if Q is in the ideal generated by P and P tilde in the local ring at that point. So looking back on our previous example, 1 minus Z1 times 1 minus Z2 divided by 2 minus Z1 minus Z2, indeed that numerator polynomial was of this form. It's just a linear combination of P and P tilde with weight 1/2 in both cases. So by the previous discussion, if Q belongs to this ideal generated by P and P tilde, then we are going to get a bounded rational function by picking that as our numerator. So the difficulty in this theorem is in the reverse implication. So showing that if Q divided by P is bounded, then it belongs to this ideal. So there's an assumption here that the polynomial P vanishes to order 1. The situation is more complicated when P has higher order vanishing, and this can happen, but I'm going to say more about that later on. We do have a conjecture for what happens in the general case. I will state this conjecture later. Instead, I would like to talk about integrability for a bit. So let's assume that we're in a situation that we found some bounded rational function Q divided by P. And we're going to ask what happens if we take its derivative. So we know that Q divided by P typically is not a continuous function, and so it's not at all clear that the Z1 derivative, say, of Q divided by P belongs to some LT of the 2 torus. So LT of T2 stands for the usual L2 space of the 2 torus with Lebesgue measure. So this is some way of measuring how regular Q divided by P is. Of course, you can ask a local version of this question where you ask that Q divided by P is integrable in some neighborhood of a boundary 0 of P. All right, so let's look at one of our examples. So if we pick this phi here, for the form 2z1 z2 minus z1 minus z2 divided by 2 minus z1 minus z2. Well, this is a rational inner function. This is modulus 1 at every point of the 2 torus. And you can compute its derivative by hand. It's this expression. And again, you can check for which exponents t this function is an LT of the 2 torus. And it turns out that this is true if and only if t is less than 3/2. All right, so I'm going to devise a different numerator polynomial. So I know that anything in the polynomial ideal generated by P tilde is going to furnish a numerator that makes Q divided by P bounded. And so I'm going to look at Q of the form Z1 minus 1 times P tilde. So note that P tilde vanishes at 1, 1, as does the numerator, the denominator in this case, which was this polynomial 2 minus Z1 minus Z2. But I've added in some additional vanishing in that I've multiplied by this factor Z1 minus 1. And then it turns out that the resulting bounded rational function has Z1 derivative in LT, precisely when t is less than 3. So the integrability has gotten a little bit better, which intuitively speaking is coming from the fact that we're adding in more vanishing in the numerator. So there's more cancellation going on in some sense. So finally, if I pick some higher power of Z1 minus 1 and multiply P tilde by such higher powers, then I'm going to get a function that has bounded derivatives. So these numbers, 3/2, 3, and infinity, are the so-called integrability indices for derivatives of Q divided by P when P is stable. So let me make this more precise by giving the following definition. So we say that a positive number, capital T, is Z1 derivative integrability index of P if there exists a Q, such that Q over P is bounded, and T, capital T, is the supremum of T such that the partial derivative with respect to z1 of q divided by p is an LT. So the integrability indices that I exhibited here were 3/2, 3, and infinity. Okay. So let me state a theorem in this direction that we have in our recent paper. So here are the assumptions. So suppose P is a pure stable polynomial with m zeros on T2. So we know that there are finitely many zeros, and I'm listing them here in some order. And we assume, again, that P vanishes to order 1 at each of these zeros. Then we can list all the Z1 derivative integrability indices of P. And all of these indices are going to belong to a long list of numbers of the form kj plus 1 divided by kj, kj plus 1 divided by kj minus 1, kj plus 1 divided by kj minus 2, ... and so on and so forth, up to kj plus 1, and then the next one is infinity. So for at each zero, there's going to be a list of this form, and then the global list is gotten. You get the global list by taking the union of all of these lists. So because each one of these lists is a finite list, and there are finitely many zeros, there are going to be finitely many of these integrability indices. So what I haven't told you yet is what these kj's are. They are the so-called contact orders of the polynomial P at the zeros tau j. So the contact order is a local algebraic characteristic of the denominator polynomial P. And in order to tell you what they are, I need to delve into this local theory that is alluded to in my title. But before I continue, perhaps I can take a quick check if there are any questions so far. Okay. Well, if there are no questions, then let's delve into the local theory. But first, let's just check the numerology. So I can work out what this algebraic characteristic, the contact order, is for the polynomial 2 minus z1 minus z2, and it turns out that it's equal to 2. And this turns out to be the smallest possible contact order you can have in the presence of a zero. And let's see, so what do I need to look at? I need to look at kj plus 1 divided by kj. So when k is equal to 2, this is 3/2, so that checks out. The next one is going to be 2 plus 1 divided by 2 minus 1, so that's 3, that checks out. And the last one is going to be infinity, which is also included. So given that I've told you what k is in this case, and given that I've told you what this list is, the numerology checks out, but let's have a look at what contact order actually is. So this requires some of this local theory, and I'm going to switch to the by upper half plane for convenience. So this can be done with a conformal transformation. For these local questions, that's not a problem. So we are going to formulate this, all of these results for the by upper half plane. And so instead of having a 0 at the point 1, 1, I'm going to look at zeros at the point 0, 0, which is a point of R2, which in turn is the distinguished boundary for the by upper half plane. So let's look at the polynomial P. So this polynomial can be factored into a unit times k Weierstrass factors. So each one of these P1, P2, and so on and so forth are Weierstrass polynomials. So they're polynomials in one of the variables, let's say z2, with coefficients that are analytic functions of the other variable. So now when P is assumed pure stable, that is with no zeros in the poly upper half plane, in the biupper half plane, but possibly some zeros on R2, these Weierstrass factors take on a special form. And so this is going to be the technical slide of this talk, but we're going to walk through it slowly. So each one of these PJ factors can be written in the following form. It's a product over little m from 1 to capital M of Z2 plus Qj of Z1 plus Z1 to some power 2Lj times a function psi sub m. So what are these objects that appear in the parenthesis here? So each Qj is a real coefficient polynomial that vanishes at the origin and has positive derivative at the origin. So this polynomial Qj looks something like Z1 times some positive number, and then there are higher order terms. The degree of Qj is less than this number 2Lj, which appears in the next term, and Lj here is a natural number. That is to say, the Z1 to the 2Lj is Z1 to some even power. And then these psi m's are obtained from some analytic function psi, which has positive imaginary part at the origin, and psi m is psi evaluated at the root of unity, at an m, capital Mj root of unity times Z1 to the 1 over Mj. So each one of these Weierstrass polynomials, reducible Weierstrass polynomials, is of this form, and it can well happen that this capital Mj is greater than 1, so that there are 2 or more factors in this representation. So the important thing to remember is that Qj has real coefficients and vanishes at the origin. And then there's this higher order term which features a power of Z1 that is even. And let me tell you right away that this 2 times capital Lj, that's going to be contact order. So let's look at the special case when we have order vanishing 1. So that means that we can write P as a unit times 1 of these Weierstrass factors. And then this is going to look like Z2 plus one of these Q polynomials in Z1 plus Z1 to the 2L times psi of Z1. So this K is exactly the contact order. So if you do this for this example that we looked at, you are going to get K equals 2, so the capital L is equal to 1 in that situation. So what does this local representation give us? Well, there's something special going on here when we examine points of the form Z1, comma, minus Q1 of Z1. Then these first 2 terms and the representation of P1 cancel out, and we're left with this Z1 to the 2L times psi. And it turns out that this curve is a special curve that is where it is profitable to examine the behavior of P to get an idea of what's going on for bounded rational functions. So it gives you a direction to look at, which is of particular importance. So now in the general case, the representation looks something like this. So you might have multiple factors Pj, and each one of these factors can in turn be quite complicated. And this leads to some complexity in the general case where you have order of vanishing that is greater than 1 at a boundary 0. So in both of these theorems that I formulated, the assumption was that the fundamental polynomial P vanishes to order 1. So I said that there's a conjecture for what happens in the general case, so let me tell you about that conjecture. So let us define for a P with the Weierstrass factorization that I displayed, let us define the following product ideal. So you generate an ideal local ring at the origin by looking at products of this form. So you look at Z2 plus QJ, comma Z1 to the 2 LJ. So these are taken from this representation, and you take power M, capital MJ, and then you multiply together over J. So this is a product ideal. And this ideal is in general larger than the ideal just generated by P and its reflection polynomial P tilde. And the conjecture that we have for the general case is that a rational function of the form Q divided by P should be bounded at the origin precisely when the numerator polynomial is drawn from this product ideal. So this looks like a conjecture that's maybe supported by little evidence as has been discussed in this talk. But in our paper, we actually prove this conjecture if P vanishes to order 2, or if there's an ordinary multiple point at the origin. And this just means that all these Weierstrass factors are distinct. So you have as many Weierstrass factors as you can expect from P. But in the general case, this conjecture is open. We think that it's true, but we have not been able to establish it so far. So that is the material that I prepared for this talk. I realize now that I've gone through it quicker than I expected, but that just means that we have more time for questions. So thanks very much.
Thank you, Alan, for a wonderful talk. Let's think speakers together, and questions, comments, suggestions. Okay, if there are no questions, let's thank Alan again.
Thank you.